All right, time for another DrivePhysics.com, DebatePhysics.com also, video presentation. So in the Wikipedia sucks category, covering all the basic subjects of physics, hopefully, in the next, whatever, 20 more days or so. Maybe I'll do it forever, who knows. It's a good way of making the comparison between reason and logic being applied and pure dogma, just absolute dogma. Old fairy stories, new fairy stories. They just tell a fairy story. They all say, we believe it, therefore you have to believe it. We've taught all our disciples the story they're supposed to tell. You can just go to the different, biblical book, the book of Huygens. Then it becomes the book of Feynman and the book of Einstein and the book of whoever who believes this crap. And that's all it is crap. It's junk science. So we'll be dealing with the words conservation of energy as Wikipedia understands that phrase. And they just don't really understand it at all, which will become obvious and apparent. And so leave us proceed. All right, so obviously I would say that energy is like this stuff in the screen over here. Okay, it's like that. And the idea is you have to conserve this stuff. You can't kill it, you can't destroy it, you can't make it go away. So kind of like the matter, you could say that there's cells in my body, billions of them, and they're made out of atoms. Okay, trillions of them. All right, and all of those atoms have a history. They were here, likely on the surface of the Earth for most of them, 1 million years ago, and 10 million years ago, and 100 million years ago. These atoms were here, on the surface of this planet doing stuff. Yes, some of them are new because they shot out of a volcano or something, 100 years ago or 10,000 years ago, and they ended up drifting into the cycle that became me. The vegetation and the animal products that my parents ate and all of that kind of stuff. But yes, this is the truth. The truth is the matter is indestructible, and so is the energy. And so the idea of conservation of energy is a really old idea. And I don't see much point in going, itemizing who it occurred to first, because you're not going to be able to do that anyway. All right, so let's just do a little context, and then we'll move on to the video. What the hell's wrong? Should be able to do this. Yeah, it's not asking much, computer. So this is what conservation of energy is fundamentally about. I mean, you have to get past this hurdle. You don't get past this hurdle, no point in even talking about it, really. I mean, just no point at all in talking about it. Because there's two basic theories, this Newtonian one, Galilean, Descartes, Newtonian, guys before that, guys after that, who basically say, yes, this is what happens in the universe. A mass obtains a velocity. And some of that's in the form of force, as we've gone over, but basically we're interested in the stuff, the matter moving, not so much interested in the force moving, but whatever. I mean, gravity and all that stuff, it's all invisible, you can't really see it. And its effects are the thing that's more obviously relevant to us than it itself. But anyway, and so the idea is it's just a quantity. This is a quantity, mass times velocity. So kilograms now, and meters per second. And that's all you need to know. Kilograms, meters per second. So this is the new version. Okay, this was first. It's not really new though, right? It's introduced before Newton, in 1665 or 8 or something, by Huygens. So Huygens, this is Huygens' theory, this mv squared thing. Yes, it wasn't very rational theory because he basically said both things are conserved. And as I'll illustrate in two simple examples, that can't happen. All right? There's no way you can conserve both of these quantities in any circumstance where you're transferring energy from the little stuff to big things, or from big things to little things. Anytime you have a change in the mass, where you're going to give the momentum, this quantity, to something that has a smaller mass or something that has a bigger mass, you're going to break one of these two theories. Can't be conserved. So the real argument is whatever one is consistently conserved is going to be the winner, and I would argue that every experiment demonstrates momentum to be conserved, every credible experiment, that's the real energy in the universe. This is the formation, this is the formalization of energy. Okay, this is a fable, this is a fake and a phony and a fraud, and it kind of has an obvious look of it. Momentum with a velocity squared. You can't square a velocity. A velocity is an arrow. You can't square it. It doesn't have dimensions. It's not a three-dimensional object. It can't be any of those things. It can't be a square or a cube. And the 1/2 is just an arbitrary excuse to qualify the excesses created by this velocity squared. The numbers get crazy, and so you need something to cut it in half because it gets crazy. The numbers are silly. All right, so let's illustrate the silly numbers. And why this is the only subject, really. You're going to talk about conservation. You have to talk about the fact that you have to fix this problem. This is a big problem in physics. All right, so the simple example is 5 mass. Okay, you bang it into another 5 mass. And now you can do that lots of ways, right? You can just drop 5 on top of it. You can do lots of different ways of doing it, and they have different efficiencies. And the fact is that the experiment, which you end up with, is a 10, okay, mass. And you were going 10 velocity here, and you're only going to go 5 velocity here, okay. And so if you do it inefficiently, okay, and not conserve the momentum, only get 85% of the momentum because you banged it up and you broke its wheel or you did something to make it inefficient. But the fact is you can do it so it's really efficient. You can drop it very gracefully, you can add the weight very gracefully, and you can actually conserve 99% of the momentum. So only lose a tiny fraction. So this is only 4.9. Okay, instead of 5V, it's 4.9. You lose a little tiny bit. But the fact is you have to lose whatever amount of this you lose, momentum, you're going to lose twice, half of that in kinetic energy. So if it's 99, say if it was only 75%, say if I did the experiment, I only had 75% efficiency in the momentum, it means I'm only going to have 37%, okay, of the kinetic energy. I'm going to lose more than half, a substantial, monstrous amount. I'm only going to conserve 37% of the kinetic energy. But if I get to 99% of the momentum, I automatically have to lose at least 50%, okay, of the KE is destroyed, lost. There's absolutely no evidence. The heat and any kind of motion, that's in this loss already. You're already saying this loss of the 1%, the 1% loss of the momentum is already describing the heat. That's how you lost the 1%, is you made heat, or you made sounds, or you made sparks, or you broke a piece off. That's the 1% already. It's already in the calculation. So you can't use that as an excuse for this 50%. This 50% is merely the consequence of this formula. There's no way to take the velocity decrease, okay, and that's what you have, a huge velocity decrease, and not recognize that because of that squared term, okay, that velocity decrease is going to be huge. And it's going to cost you a ton of energy. So even though you increase the mass, okay, the fact is this squared velocity means that the velocity is so much more powerful. So that, they can make the mass arrow go up and the velocity arrow gets huge because it's squared. All right. So the experiment basically proves which one's conserved. Momentum's conserved, and kinetic energy is a nonsense. It doesn't happen. It's not real. Now, a more gross example is the ballistic pendulum, where the bullet, we could say it has 5,000 joules. Okay, we could say it's 5,000 watts. I like that much better. It's much easier for me to understand energy in terms of watts, because that can be heat, that can be spinning motors, that can be lots of things, watts. It's in the environment in lots of ways. And then you bang it into a big giant mass, You absorb the bullet, and you try to do it as efficiently as possible again. And yeah, you can conserve, say, 97% of the momentum. So you can take the bullet's momentum, its mv, its mass, and its velocity. You can convert it into an mv here, a mass times a velocity, and conserve 97% of it. And what does Professor Lewin acknowledge? You lose 99.94% of the kinetic energy. Gone. And again, the same argument is going to be made that all you lost was 3% in heat, okay, and motion, useless motion of the clay. So the clay inside the ballistic pendulum yet moved in directions that didn't cause linear motion in the direction you're looking for. And it warmed the clay, and it did some things, and that's the 3% you lost. That's the 3%. The 3% is in those losses. So you're still stuck with this monstrous destruction of energy. Clearly, you can't conserve it. Clearly, it makes no sense. It's clearly obvious that the bullet only has the same energy as the recoiling gun, that all it really has as real energy is its momentum. And all you're doing is conserving the momentum. All right? Kinetic energy is not real energy. It's not real. It can't heat anything. It can't move anything. It can't do anything. It's a useless number. The real number is whatever, 50 watts, not 5,000 watts. All right. Yeah, that should be enough as a context. I could use spaceships, okay? You have a spaceship in space, you throw the bullet out one side, and then you throw a recoiling gun, the equivalent of. So you have a spring device, you shoot a bullet out, very fast. You shoot a gun out the other side very slow, okay? 1,000 times more mass goes out one side of your ship at 1,000 times slower speed, is the simple argument. And physicist Michael has conceded the spaceship doesn't turn. So even though you have 1,000 times more energy going out one side of the ship than going out the other side, by their definition, by that stupid formula, 1/2 mv squared, the fact is the ship doesn't turn. Now, what is better proof that it's not real energy than the fact that it can't move matter in space? It can't move a piece of matter where it's not, there's no friction, there's no this, there's no that, there's no problems, and it can't move the matter. If it can't move the matter, it's not real energy. Come on. This is not even close to mentally challenging. All right, so from the idiotic, terribly written, garbage Wikipedia page. Okay. All right, the law of conservation of energy states that the total energy of an isolated system, again, just this whole idea we can do that, where, the isolation is, is best we can do. We can't get rid of the atmosphere. We can't do this, can't do that. I mean, in some cases you can, obviously. You can pump the air out of a vessel and then drop a feather and a hammer. Anyway, it remains constant. It is said to be conserved over time. So again, what's the point? What's this word energy mean? Right? In physics, energy is the qualitative property that is transferred to a body or to a physical system recognizable in the performance of work and in the form of heat and light. Energy is conserved quantity. The law of conservation of energy. See, this is a nothing answer. Is it MV or is it momentum? Which one is energy? Okay, the kinetic fake stuff or the momentum real stuff? In the case of a closed, and they don't get to that subject here. They just jiggle around here, talking this jargon, and they never resolve the fact that they have this huge, gigantic duality in the room, where they're claiming basically there's two basic definitions of mass moving. One of them's momentum, and one of them's the kinetic energy theory. They're two different definitions of the same thing. In the case of a closed system, the principle says that the total amount of energy within the system can only be changed through energy entering or leaving the system. So you have to add something new, or you have to let something drift out, obviously. So you have to let it leak out of the system to lose energy. You can't lose energy just because the things banged into each other, because every time they bang into each other, they're going to transfer energy. Energy can neither be created or destroyed. Same with matter, factually. Rather, it can only be transformed or transferred. So transformed, I think, is a kind of a bullshit word. It's always just transferred. One object has contact in some way, manner, or other with another object, and it transfers its momentum. Okay, or transferred from one to the other. For instance, chemical energy. So this is a really bad example because we know this chemical energy thing is very complicated in the sense it has to do with how much pressure is inside of atoms. But anyway, I mean, they should use the simple example. For example, a train going 10 miles an hour. That's what you should do. For instance, chemical energy is converted to kinetic energy. So there's no conversion. It's inside the chemistry has the energy stored in it. It's a force. It's stored in the atoms in the sense of being stored in the atoms in the form of a capacity for electrons to be shot and moved. Okay, when a stick of dynamite explodes, if one adds up all the forms of energy that were released in the explosion, so you have one form of energy, okay, and it's the motion, it's expanding atoms, all right, essentially. So you have ions and probably some electrons and protons are being broken off, but basically they're just taking up more space, so they expand the size of the atoms. All right, such as kinetic energy and potential energy of the pieces, as well as the heat and sound. One will get the exact decrease of chemical. One will get the exact decrease of chemical energy in the combustion of the dynamite. So they're basically saying, look, a spring compresses. Okay, then you expand the spring. It doesn't matter whether you put little things in front of the spring or big things in front of the spring. You're going to get the same energy back. Now, clearly, the argument is, well, what's your expectation? Okay, what does the experiments really say? Do you get back kinetic energy or do you get back momentum? Which one is conserved? So if I push it with a certain amount of momentum, am I going to get that momentum back? That's the question. And physics won't answer it. Because the truth is you're going to get the momentum back. You're not going to get the kinetic energy back. You change the size of the objects. The kinetic energy theory is going to create free energy in the light objects, and it's going to destroy energy in the heavy objects. Classically, conservation of energy was distinct from conservation of mass. Well, there shouldn't even really be an argument about once we got to an atomic theory that you can destroy mass. So, not really a useful statement. In the sense you can't destroy it in the sense that you still have electrons and protons. You can't destroy these elemental pieces. However, special relativity, so why would they get into special relativity when you're talking about conservation of energy? I mean, it's really an abstract subject. It really doesn't relate to anything in really anywhere. I mean, there's no place where this matters except inside of an accelerator or something. So why even bother talking about it? Shows that mass is related to energy, and vice versa, which again isn't really true. Okay, I mean the equation is just telling you in a certain form mass equals c squared. Yeah, I mean energy equals the mass times the speed of light squared, and it's not an explicit definition either. It's just saying the mass times the velocity of elemental particles. Obviously, it contains a lot of energy. That's why there's a nuclear bomb, is because you can take an atom and you break it apart, and obviously had a lot of pressure in it. So you're going to move the little bits very, very fast, and they're going to be capable of moving bigger pieces, some slower velocity. But it really just has to do with the compression of matter. It has to do with pushing electrons and protons together. That's where the energy is coming from. It's not coming from the mass itself. The equation representing mass energy equivalence, so that's also just garbage anyway. The science now takes the view that mass energy as a whole is conserved. So this is just kind of a silly statement, right? So we know it's not. Kinetic energy isn't conserved. So if you're going to keep using the word kinetic energy, you have to concede it's not conserved. So why are you pretending it is when it isn't? All right, theoretically, this implies that any object with mass can itself be converted into pure energy. So it implies it. Yeah. And the argument is no, electrons and protons inside a nucleus can be converted into electrons and protons moving. But if I just take electrons and protons and scatter them in, very unpressurized circumstances, they don't have any pure energy. Okay, and vice versa. However, this is believed to be possible only under the most extreme of physical conditions, like inside of a sun, such as likely existed in the universe very shortly after the Big Bang. So that's they have a whole page devoted to shortly after the Big Bang. So that's all such speculative nonsense. Or when black holes emit Hawking radiation. So here you're teaching a kid, let's say, by saying, oh, go read the Wikipedia page. It's talking about something very basic about whether you have to conserve whatever this stuff is that causes stuff to move. And here they are already talking about this bizarre abstraction where you're required to believe their Adam and Eve story about the Big Bang. Given the stationary action principle, which who cares, conservation of energy can be rigorously proven by Nether's theorem. Okay, and it's just bullshit. Okay, so again, it's to call it rigorous, to call it meaning anything is just an absolute nonsense. It's just a mathematical circular math. As a consequence of continuous time translation symmetry, which just means absolutely nothing. Garbage in, garbage out, circular, circular, circular. So why is this in here? You don't need any of this to understand the basic concept that force can't be destroyed and that matter can't be destroyed. And so therefore you have to conserve both of these things because they can't be destroyed. They can't be eliminated. Again, it's so much simpler if you do understand electrons and protons as dead pieces of matter. That is, they don't have any self-propulsion mechanism. They have to be pushed by a force that actually is engaged in the process of pushing them. All right, they have to have, it's like being in one of those Japanese carts and there's no guy pulling your cart. If you got no horse, you're not going anywhere. The horse has to stick to you or you're just going to be standing still. A consequence of the law of conservation of energy is that perpetual motion machines of the first kind cannot exist. I don't know what a second kind is. And so clearly you can't make a machine, all right, that can perfectly, efficiently do a transfer of energy. And that's all that's really saying. So theoretically, in space, perpetual motion probably is possible because you can create a system that is frictionless. You could argue that protons and electrons are in a frictionless environment. They can't create something called heat because they would be the heat. So if they actually do bump into each other, they do it with 100% efficiency, not some 99% efficiency. And it's only because we can't do something with 100% efficiency, we can't build a physical device that has 100% efficiency, that there's no perpetual motion. But the bigger subject is, can you create free energy? Can you make something have more energy? And that clearly you cannot. So we can never make a device that can have enough energy, like 110%, so then it can do something, then it can compensate for the frictions, the losses. That is to say, no system without an external energy supply can deliver an unlimited amount of energy. Things can tick forever. So I'm just saying it's wrong to say that you couldn't put a pendulum somewhere in a certain environment where you initiate its motion and there are zero losses. I mean, it's theoretically attainable to have a lossless system. So again, it's to confuse perpetual motion with free energy is a mistake, and they're just implying it all over the place here. Go ahead and make that mistake. To its surroundings, depending on the definition of energy, conservation, depending on the definition of energy. Why should we have a depending on the definition of energy? Shouldn't we establish one or the other one? Why don't you make a page describing, well, if momentum is energy, this is what will happen, and if kinetic energy is energy, this is the truth. But you really can't, there's no rational way you can defend the theory because, again, the ballistic pendulum proves it. The spaceship proves it. Your math says you have to lose half the energy. There's no evidence you lost it to anything real. It disappeared because it's mathematically required to disappear. Conservation of energy can arguably be violated by general relativity on the cosmological scale. So again, just more. Why throw that kind of crap in there? This theoretical, highly theoretical, not even close to anything proven by evidence. All right, so I don't know if this ancient stuff is much good, but we'll go through it anyway. Ancient philosophers, five back as some kind of whatever, 550 BC, had inklings of the concept of conservation of some underlying substance of which everything is made. So obviously, yes, it occurred to people throughout history that they looked at the way the world worked and they said, you know, the rock falls down, it goes into the stream, it turns into sand, it ends up in the ocean. The ocean ends up making rocks that look like rocks made by the ocean, you know, the sedimentary rocks. It looks like a cycle to me. So the fact that they figured out that it's cyclical, okay, hardly a big, giant, hugely mysterious observation. However, there is no particular reason to identify their theories with what we know today as mass energy. For example, thought it was water. All right, Empiric, whatever, wrote that in his universal system composed of four roots, earth, air, water, fire, nothing comes to be or perishes. So these are nice quotes, and it's just an idea that, okay, it occurred to lots of people that the world has a certain amount of stuff in it, and the amount of stuff isn't going to change. We can't eat it away. We can't, drink it away. We can't make it disappear. All right. Instead, these elements suffer continual rearrangement. And so exactly correct. So, 2,000, over 2,000 years ago, 2,400 years ago, humans were doing better physics than physicists are doing today. Okay, Empiricus, on the other hand, believed everything in the universe to be composed of individual units of matter, well, very clever, an ancient predecessor to atoms, and he too had some idea of the necessity of conservation, stating that the sum total of things is always such as it is now, okay, and such it will ever remain. So you got all these examples of people living in the most crude, bleak, dark environments, and they could light this candle and say, it all looks like it's a closed system. In 1605, the Flemish scientist Simon Stevens was able to solve a number of problems in statistics based on the principle that perpetual motion was impossible. You can't even imagine where somebody would think it was possible. What mathematics made it possible that this guy had to fix? There shouldn't be any mathematics that made it possible. Where do you invent the extra mv? I mean, the quantity of motion thing works so well. All right, in 1639, Galileo published his analysis of several situations, including the celebrated interrupted pendulum, which can be described in modern language as conservatively converting potential energy into kinetic energy and back again. So again, there's no conversion of any energy. You're having your energy taken away from you by the gravity, and then it gives it back to you in falling. That's all that happens. You lose it. You don't have any potential energy. A boat on the side of a stream does not have any potential energy. You have to put it in the stream for it to have energy, to gain energy, to take the energy from the stream. We take energy from gravity when we're falling. Essentially, he pointed out that the height of a moving body rises is equal to the height from which it falls. So it's a very valid, observation that there's even if you have a pendulum and you put an impediment in there and the pendulum swings faster, it still only goes to the same height it would have gone to if you allowed it to swing on the larger arc. So it's always the same height. And use this observation to infer the idea of inertia. So we don't need this inference that there's such a thing as mass, okay, inertia. The remarkable aspect of this observation is that the height to which a moving body ascends on a frictionless surface does not depend on the shape of the surface. So obviously, if you had an idealized surface that lost no energy to that surface, it would never be losing any of its potential energy. That means it wouldn't be losing any of its real energy. So yes, if you could put a car on a non-frictionless surface, it won't lose any energy either. So you could drive 10 miles or 1 mile, and as long as you went the same force, the same height against gravity, you could do both of them with the same fuel. In 1669, a roller coaster kind of thing. It's just a demonstration of a roller coaster, and the more efficiently you make the roller coaster, the longer and longer you can make the roller coaster. In 1669, Christian Huygens. So this is the key event. Okay, so I was wrong, in a sense that I didn't think Huygens overtly stated mv squared. But he did. He stated it was conserved. In 1669, he stated that is conserved. They should have a quote from him. So they quoted the guys from 2,000 years ago. Why aren't you quoting Huygens? All right, so Huygens was the first one to introduce this nonsense. And Leibniz just stole it, for fuck's sake. He just plagiarized Huygens. And it's clear in the history that he hung out with Huygens for a number of years. I believe when he was in France. But anyway, they ended up both being there for some reason. All right, anyway. In 1669, Christian Huygens published his laws of collisions. Among the quantities he listed as being invariant before and after the collision of bodies were both the sum of their linear momenta, which obviously isn't true with things with wheels, as well as the sum of their kinetic energies. So how could it possibly make sense? Colliding bodies, okay, anytime you collide a light thing with a heavy thing, you're going to have to not conserve one of the two things. It's impossible to conserve both the kinetic energy and the momenta, because that squared term, the squared term on the velocity, means you cannot possibly conserve, all right, if you're changing the size of the masses. However, the difference between the elastic and inelastic collisions was not understood at the time. So I don't believe that Huygens didn't know the difference between bumping two blobs of clay into each other and bumping two hard pieces of glass into each other. I'm sure he understood the difference. It led to the dispute among later researchers. So I don't know who they are, the Newtonians? Okay, as to which of these conserved quantities was more fundamental. So this is the whole page right here. This is the only thing they should be talking about right there. That's it. That line. That's all that matters here. Because there's no point in talking about conservation when you can't define what you're conserving. And physics isn't defining what it's conserving. It's idiotic to say you can conserve both. You can't. And the fact is, the one that's more fundamental is the one that's always going to be conserved, and that's going to be momentum. So I could quote Professor Lewin: nature can deal with kinetic energy one way or the other, but nature can't finagle momentum. You can't make momentum disappear, and you can't make momentum appear out of nowhere. It can't be done. You can't make free momentum. In his hologram oscillatorium, he gave a much clearer statement regarding the height of ascent of a moving body and connected this idea with the impossibility of perpetual motion. So ironically, as we'll get to with the Deschardelet woman, one of her people was a big fan of chasing perpetual motion theories. Anyway, let's stick with Huygens. Huygens' study of the dynamics of pendulum motion was based on a single principle, that the center of gravity of a heavy object cannot lift itself. All right. And clearly Huygens was an expert at this pendulum crap. He was a clock maker, a clock designer, you got to say. Did a lot of brilliant work, blah, blah, blah. But frankly, V squared is a stupid idea. All right, between 1676 and 1689, all right, so I don't know where they get the 1676 number from, because I couldn't find this earlier Leibniz reference. Gottfried Leibniz first attempted a mathematical formulation of the kind of energy that is associated with motion. He just reiterated the same exact statement as Huygens. Huygens' statement was velocity squared is the quantity conserved. Huygens is just saying the same exact thing 20 years later. Okay, using Huygens' work in collision, Leibniz noticed that in many mechanical systems of several masses m with each with velocity v1, so here it is, mv squared, was conserved. And this is the part that you're just saying, what are you talking about? So long as the masses did not interact. How can you lose energy if nothing's interacting? Of course it's conserved. If nothing hits anything, then the same object that had velocity keeps its velocity. The heavy thing keeps its velocity. The light thing has its velocity. If they don't interact, you're not exchanging the energy. You're not testing the energy. You're not doing anything. So how could that make any sense? So long as the masses did not interact. What possible sense can that make? How can you talk about conservation when you're not going to test the conservation by forcing it to interact? You can only lose your energy by interacting. You can only exchange it by interacting. You have to interact to exchange it. Just too silly. He called this quantity the vis viva, the living force, or living force of the system. The principle represents an act. So, and again, he meant living force in the real. He believed in solitons, and that means they have souls, not that they're made out of shoes. And monads, which are, I don't know whether, monads are a step below, so they're like slaves. Solitons are really cool. Monads are trying to be cool, but they just aren't there yet. The principle represents an accurate statement. I don't even know what this means. The principle represents an accurate statement of what? In non-interacting systems, none of the energy is exchanged, therefore it's completely conserved. Duh! Of the approximate conservation of kinetic energy. So again, it's not conserved. Kinetic energy is not conserved. In situation where there's no friction or no contact, or no exchange. But in every circumstance where you exchange the energy of a light thing going fast and you could try to convert it into a heavy thing going slow, you have to lose a ton of energy. And if you do the vice versa, you're going to make a ton of free energy. The gun makes free energy by their theory. The gun recoil is 2 joules. The bullet's launch is 2,000 joules. You can understand the gun is making free energy because of the third law. Okay, many physicists at the time, including Isaac Newton, held that conservation of momentum, which, this isn't even written well. Many physicists at the time, including Isaac Newton, held that the conservation of momentum, which holds even in systems with friction, as defined by the momentum. That's not a rational sentence. You should just say that that Isaac Newton believed momentum was energy and that momentum is conserved. Now, in systems with friction is nonsense. Obviously in friction systems, you're going to have to lose some portion of your momentum to heating the ground or doing some other thing. So that was just, I don't think Newton believed that. I don't think this is a quote of Newton. I think this is a paraphrase of Newton, and I think it's wrong. Which holds even in systems with friction. Obviously it can't hold even in systems with friction. Momentum creates energy, heat. It creates anything that happens. A piece breaks off, it means that's a piece of the momentum gone. A bowling ball hits a pin. The pins are taking the energy. Okay, the bowling ball can't hit the pin and keep going with the same momentum. They're exchanges of its momentum. All right. As defined by momentum, and then it says mv, okay, is the simple statement, was conserved vis viva. What does that even mean? This is a colon here. Was conserved vis viva. This doesn't even have any continuity. MV was conserved vis viva. And vis viva is living force. It's not MV. So what are they doing here? What is this gibberish? Okay, God damn it. It was later shown that both quantities are conserved simultaneous given the proper conditions. Right, and the proper conditions is that you're not banging into a mass that's a different mass. If you bang into a mass that's not the same mass as you are not going to conserve both. Such as in an elastic collision. An elastic collision was something that weighs the same as you do. Because if it's an elastic collision with something that weighs more or less than you're not going to conserve the kinetic energy and the momentum. Can't happen. I mean, the clear fact is, I'm going to just make the statement, you're not going to conserve the kinetic energy and you're always going to conserve the momentum. In 1687, Isaac Newton published his Principia. So this is the same year that Leibniz published mv squared as an idea, okay, a regurgitation of Huygens, as it turns out, which set out his laws of motion. So clearly Newton was aware of all that, I imagine, to some extent. I mean, obviously it's hard to say. Did Newton know that Huygens had suggested that mv squared was conserved? I don't know. It was organized around the concept. I mean, he didn't point it out that Huygens was wrong. It was organized around the concept of force and momentum. So clearly that was the point, is that everything he talked about was basically a verification of the fact that force is momentum. And the fact is that's all we have to exchange. The quantity of motion is momentum, and that is definitely conserved. Clearly the third law is basically saying you have to conserve it. However, the researchers were quick to recognize that the principles set out in the book, while fine for point masses. This isn't about point masses. This is about watermelons. It's about elephants. It's about moons. It's about apples. Bullshit point mass nonsense. Were not sufficient to tackle the motion of rigid and fluid bodies. Bullshit. They just didn't know exactly how what the fluid bodies were made out of. But Newton clearly understood that if he dropped a piece of clay on the table, he clearly understood that, well, the energy is now moved the clay in all kinds of weird directions. So it's misshapen the clay. And that's where the energy went, to reshaping the clay. They all knew that. Some other principles were also required. There's no requirement for any other principle. So that's just a big, fat, juicy nonsense point. There was nobody who said that. Nobody argued that against Newton. Newton completely won the argument entirely. There weren't anybody objecting to Newton at all. There just wasn't. There was Leibniz. That's it. Okay, by the 1690s, Leibniz was arguing that conservation of vis viva and conservation of momentum undermined the... So how could he say this? How could this make any sense, that he's talking against his own theory? By the 1690s, Leibniz was arguing that conservation of vis viva and conservation of momentum, so he's saying both theories, undermine the then popular philosophical doctrine of, what the fuck is this? Interactionalist dualism. This is like some cult religion. All right, it's a theory in the philosophy of mind. This is in a physics Wikipedia page. This religious mush they're shoving in conservation of momentum. Like there was a whole big giant bunch of scientists who were caught up in this nonsense. Is a theory of the philosophy of mind, which holds that matter and mind are two distinct and independent substances that exert causal effects on one another. I mean, what a pile of nonsense. So clearly Leibniz was a religious kook who thought, we could, make ducks quack with our brain. We could just quack, duck, quack. I'm thinking quack, you should quack. I mean, quackery, quack, nutty. And so he's pissing on his own theory. I don't remember him doing that, frankly. He was defending vis viva right up to his death because he was using the analogy in the letters to the king of dropping 4 pounds, 1 foot is the same as 1 pound, 4 feet. So he was using that argument, right up to his death. So this sentence is a nonsense. During the 19th century, when conservation of energy was better understood, so what a lie, okay? I mean, it's just so silly. When you just pretended there isn't an energy duality. They just decided, well, let's just pretend the duality doesn't exist. That's all they did. That's all the 19th century offered as a solution. Let's just pretend it doesn't exist. That we don't have two completely different concepts, two completely different definitions. MV squared, MV. Two completely different definitions of what makes stuff move in the universe. Leibniz's basic argument would gain widespread acceptance. Okay, so it wasn't Leibniz's argument. I don't think that has widespread acceptance. Frankly, if I ask a physicist, do you really think the impact weight of 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet? It only has twice the velocity. It was only in the gravity twice as long, and you think it has 4 times the energy? If physicists are going to be that overtly illogical, anyway, some modern scholars continue to champion specifically conservation-based attacks on dualism. I don't know what dualism they're talking about here, like there's any kind of dualism, this mind-matter bullshit religion talk. Why is this a subject on a physics page? This is not a subject. While others subsume the argument into a more general argument about causal closure. Oh, what could this mush mean? Causal closure is a metaphysical theory. Okay, it doesn't have anything to do with physics. It has to do with imagination and love and God. Okay, of nature, of causation in the physical realm with significant ramifications in the study of metaphysics and the mind. What does that even mean? It's not even a rational thing. It's a theory, okay, about the nature of causation in the physical realm with ramifications to the study of the metaphysics and the mind. How does this closure take place? How do you take water's going over the waterfall? Now, how do I turn that into a mind effect? My mind is making the water fall over the waterfall? Oh, this is so goddamn ridiculous. All right, in a strongly stated version, physical causal closure says that all physical states have... Oh, damn. Well, I guess we're going to have to go find that. And where is this? Oh, jeez. We're going to have to go look at that. All physical states have only one physical causes. Only physical causes. Well, that's pretty simple. Why didn't they just say that? Physical effects have only physical causes. Wow, there you go. That's perfectly sensible. Oh, shit. How is that about metaphysics? Oh, it's just a clear statement that there's no God and there's no magic. Oh, okay. So that's, we have to sit there and account for it for some reason. All right. So anyway, so the causal closure thing is perfectly reasonable. Now, I don't know whether there's any point going in this Bernoulli stuff, because this really wasn't about, the Bernoullis were brilliant, but this mush is nothing. All right, well, anyway, the law of conservation of vis visa was championed by the father and son duo, their whole family. There was like 25 Bernoullis. Anyway, the former enunciated in the principle of virtual work. Oh, that's just not very good. Arises in the application of the principle of least action. Yeah, see, this is where they just use gibberish. As used in statistics, and so in idealization. So they're just talking about idealizations. In the full generality in 1715, while the latter based his Hydrodynamica, published in 1737, on the single vis viva conservation principle. So we know it's not conserved, so clearly you have to be pretty ignorant to sit there and pretend it's conserved, because it isn't. All right, Daniel's study of loss of vis viva. So he's conceding the loss of it. Of flowing water led him to formulate the Bernoulli principle, a key concept, fluid dynamics, that relates to pressure, speed, and height. Okay, so that's that flapping thing in the breeze thing, which asserts the loss of the loss to be proportional to the change in hydrodynamic pressure. So this is a bunch of complex physics about fluid motions, which really gets into a lot of, turbulence, all this kind of stuff. This is way too complicated. Daniel also formulated the notion of work and efficiency for hydraulic machines. So that's just water pressure, and that, frankly, you don't have any excuses for a bunch of losses. And he gave a kinetic theory of gases and linked the kinetic energy of gas molecules with the temperature of the gas. So he linked it in what way? I don't think he did do that, frankly. It's just momentum. The focus on the vis visa by the, continental physicists eventually led to the discovery of stationary principles governing mechanics. I don't know what stationary would mean. I mean, mechanics is about non-stationary. Well, anyway, such as D'Amberett's principle, Lagrangian and Hamiltonian formulations of mechanics. So I know the Lagrangians and the Hamiltonians that's with all this mv squared bullshit, and that's where all the math goes south. All right, finally, de Chatelet. This is where the big lies start being spewed. So anyway, proposed and tested a hypothesis of conservation of total energy. So again, she didn't test anything. She's just testing whether she saw that Newton said conservation of mv and Leibniz said conservation of mv squared. Okay, and Huygens, and she said, well, I'm going to find out which one's true. Perfectly reasonable thing to do. Now, she was tutored by a Leibnizian, so that's part of the catch here. So he actually sued her for plagiarism, which is kind of funny, right? So a Leibnizian tutored her, somebody who was completely thought, the only form of energy was mv squared. As distinct from momentum, inspired by the theories of Gottfried Leibniz, inspired by her tutor who had been inspired by Leibniz, she repeated and publicized an experiment originally devised by Wilhelm Gravesand. Okay, now the simple truth is this is a shitty experiment. So he's dropping round things onto a clay surface, and the trick is he's making the round things big enough that they don't penetrate into the clay. They just dent the surface of the clay. So he's dropping a round surface into a linear piece of clay. Now, if you're a little bit smart, you can figure out that the round surface means the bottom is very flat and the side is very smooth going up. So that what you're really doing is the deeper you go into the clay, the more you push the clay sideways. But the initial impact is flat. It's a flat thing hitting the surface. So the deeper you go, the more you're pushing clay sideways, and the less deep you go, the more you're just pushing one way down. So if you don't go deep, then you did all downward pressure, which means you had to push the clay down and then push it sideways, two motions. Where if you're pushing it off the sides, then it's only one motion that way. So huge, it's just a debunkable experiment. It's not a good way to test. It's deceptive. Things will penetrate further because you haven't passed the perimeter of the arc. Once you've put them further down, where they're both through, where their largest dimension is through the clay, then you have an equal contest. But before you go deep enough, that way it's halfway through the circle, the sphere, you're cheating. Because the one with less energy will substantially have less energy because it's more friction, essentially. So it's the same argument as rolling something at one velocity and then rolling something at twice the velocity. The one velocity object incurs much more friction per unit of time than the per unit of distance, than the other object. And so it doesn't travel as far because it's losing more energy to friction. It's essentially the same argument. It's junk science, it's pseudoscience, it's show science, it's not real science. Okay, so anyway, in 1722, in which balls were dropped from different heights into a sheet of clay, soft clay. So again, they weren't dropped so they penetrated through the clay. They were dropped so they dent the clay. All right. I've seen the drawings. They're just dents in the clay. Each ball's kinetic energy, as indicated by the quantity of material displaced, so you're just talking about what kind of little crater it left, was shown to be proportional to the square of the velocity. So yes, the faster objects were able to penetrate the clay further because they had they were able to get through the surface of the clay. What's the right way to say it? The heavy objects going slow didn't get deep enough into the clay to take advantage of the pushing sideways thing. All right, the deformation of the clay was found to be directly proportional to the height at which the balls were dropped. So again, it's just an illusion, okay? Just like rolling things in friction. I roll something twice the velocity, it goes 4 times the distance. It's not because it did 4 times the work in terms of creating 4 times the heat into the road. It only creates twice as much. It only lost 2 units of energy to friction. And it only takes 2 units of time. 4 units of distance in 2 units of time is not 4 units of energy. Equal to the initial potential energy. Okay, some earlier workers, including Newton and Voltaire, who had believed in energy. So that's funny that they include Voltaire. He wasn't really, he's really not in the same class as Newton. He wasn't the creator of ideas. He was a writer who showed ideas. Including Newton and Voltaire, had believed that energy was not distinct from momentum and therefore proportional to velocity. Let's see. Had believed that energy was not distinct from momentum. So why wouldn't they just say the positive thing instead of that? Why didn't they just say believed energy was momentum and therefore proportional to velocity? According to this understanding, the deformation of the clay should have been proportional to the square root of the height from which the balls were dropped. And again, that's only because if you don't do science. So if you're ignorant and you don't think about the experiment, then you can make this mistake. So if you think that I can't go faster across thin ice and reduce how much pressure and friction I have with the surface, that is, I'll put less pressure on the ice by moving quickly across it. If you don't believe that's possible, then you're a Leibnizian. If you understand that I can change how much pressure I put on the ice, and therefore by going faster I will in fact lose less of my energy to the ice, and therefore the ice will not break because I will not be placing the same pressure upon it. It will not feel it because I won't have enough contact with it. In classical physics, the correct formula is E equals 1/2 mv squared. So it's just crap that's not even classical, frankly. Okay, they didn't have the 1/2 in front of the mv squared. So when de Chardin was talking about, and all these other people were talking about, it was just mv squared, no half. Where ek is the kinetic energy of the object, m is the mass, and v is the speed. On this basis, de Chardin proposed that energy must always have the same dimensions in any form, so we know it doesn't happen. The simplest of experiments, the 5-ton train being converted into a 10-ton train, proves it doesn't work, which is necessary to be able to consider it in different forms, kinetic, potential, and heat. Just absolute bullshit. All right, so the rest is going to start to get towards Joule and cannon boring, probably, and some of this other stuff, but none of it is real science. And clearly Thomas Young's contribution was meaningless. He just used the word energy first, but whatever. So we'll get to some of that, I guess. I don't know if it matters, frankly. I mean, the real show has already been over. The fact is that people fell for the de Chardin bullshit. Okay, people were ignorant and they didn't do very good science back then. She wasn't even a scientist in the sense she was just tutored. She wasn't formally trained. And she didn't invent anything. She didn't do anything. She translated Newton into French or English, one of those two. She was really good at languages, so that was her best contribution, but her rhetoric, her logic was pretty poor. All right. So, yeah, that's probably enough. Enough for a part one, anyway. So I'll probably come back to this. But all of the subjects relate to this. If you don't resolve this momentum versus kinetic energy thing, then you're not doing science. They are not compatible theories. They directly oppose each other. They come up with different answers. They state a different truth. They're completely different theories of reality. You have to take a stand one way or the other. You can't believe in both. It's childish. It's silly. It's an insult to logic.